Tonight, we're going to talk about something that should not be possible. Right now, as you sit reading these words, our entire galaxy is falling. Not orbiting, not drifting, falling. The Milky Way, with all its 400 billion stars, with its spiral arms and dark dust lanes, and the quiet little solar system where we live, is being pulled across the universe at roughly 1.3 million miles per hour, 2 million kilometers per hour. Fast enough to cross the diameter of our planet in about half a minute. And it's not just us. The Andromeda galaxy is falling alongside us. The entire local group of more than 50 galaxies is being dragged in the same direction. The Virgo Supercluster, a structure containing thousands of galaxies and stretching more than 100 million light-years across, is being pulled too. All of it, every star you've ever seen in the night sky, every galaxy in every Hubble image, every world that might harbor life within hundreds of millions of light-years of Earth, is moving as one, falling toward the same point, falling toward something. And here is the part that should keep you awake. Nobody on Earth has ever seen what we're falling toward. Not directly, not with optical telescopes, not with the Hubble, not with the James Webb Space Telescope. Astronomers have known about it since the 1970s. They've measured its gravitational pull with increasing precision for nearly half a century. They've calculated its approximate location, somewhere between 150 and 250 million light-years from us, in the direction of the constellations Centaurus and Norma. They've estimated its mass at tens of thousands of times the mass of our own galaxy. Some calculations suggest the equivalent of quadrillions of suns concentrated in one region of space. And yet, when we point our most powerful instruments at the place where it should be, we see almost nothing. A smudge of distant galaxies, partly obscured. A hint of something enormous lurking just out of view. But the thing itself, the engine doing all this pulling, remains hidden behind a wall we cannot see through. It has a name. Astronomers call it the Great Attractor. And by the end of tonight, you're going to understand why the more we learn about it, the stranger and more unsettling it becomes. Before we go any further, if you find these journeys into the deep universe as fascinating as I do, take a moment to tap the like button and subscribe. It's a small gesture, but it tells the algorithm that quiet, careful explorations of the cosmos still matter, and it helps this channel reach more curious minds like yours. Now, let's keep going. Let's begin by understanding the scale of what we're describing, because the human brain isn't built for this. You and I evolved on a planet where the horizon is a few miles away. Our intuitions about distance, motion, and gravity were shaped by walking across savannas and watching rivers flow. The numbers involved in the Great Attractor break those intuitions completely. The distance from Earth to our nearest star, Proxima Centauri, is about 4.24 light-years. Light, which travels at 186,000 miles per second, takes more than 4 years to make the journey. Our Milky Way galaxy is roughly 100,000 light-years across. That means a beam of light, the fastest thing in the universe, needs 100,000 years to cross our own galaxy from one edge to the other. And the Great Attractor is somewhere between 150 and 250 million light-years away. The light reaching our telescopes from its general direction left there before our species existed. Before Homo sapiens, before our ancestors had walked upright, before mammals had become the dominant land vertebrates. That light has been traveling through the empty corridors of intergalactic space since long before the planet we live on was geologically recognizable, and it is only just now arriving. Yet despite that staggering distance, despite the void between us and it, something at the other end is reaching across all of that emptiness and grabbing us, pulling. Steadily, relentlessly, for billions of years. And here is where the story turns from a curiosity into something almost philosophical. Because gravity, the force doing the pulling, is not magic. It comes from mass. It comes from something. To pull a structure as enormous as the Virgo Supercluster, to drag tens of thousands of galaxies in unison across cosmic distances, the source must contain a concentration of matter unlike anything our minds are prepared to imagine. We are not being moved by a star. We are not being moved by a black hole. We are being moved by something on a scale that, when astronomers first calculated it in the 1980s, they doubted their own numbers. And then there's the second mystery, the hidden one, The reason we can't simply point a telescope at the Great Attractor and see it. The reason it took us so long even to confirm that it exists. Our own galaxy, the Milky Way, sits in the way. From Earth's perspective, the Great Attractor lies almost directly behind the plane of our galactic disk, behind a thick belt of stars, gas, and interstellar dust that astronomers call the Zone of Avoidance. It's a strip of sky that has frustrated cosmologists for more than a century. When you look at maps of the universe made from optical telescopes, you'll see a strange dark band cutting across them, a region where galaxies appear to thin out and disappear. They haven't disappeared. They're still there. It's just that our own galaxy's dust is blocking the view. And right in the middle of that blind spot, by an almost cruel coincidence of geometry, sits whatever it is that's pulling us. Imagine standing in a dark forest at night, knowing that something massive is moving in your direction. You can feel the ground tremble. You can hear branches snapping in the distance, but you cannot see what it is. Every time you try to look directly at it, your view is blocked by the trees in front of you. That's the situation astronomers have been in for decades. We know the Great Attractor is there because we can measure its effect on everything around us. We can map its gravitational fingerprint with extraordinary precision. We can chart the rivers of galaxies flowing toward it, but the source itself remains shrouded, partially seen, partially inferred, partially still unknown. Over the next several sections, we're going to walk through the story of how astronomers first noticed something was wrong with the motion of the galaxies. We'll meet the scientists who refused to accept the easy answer and kept measuring until the truth emerged. We'll look at what the latest radio and X-ray surveys have begun to reveal behind the Zone of Avoidance. We'll talk about the discovery, only made within the last few decades, that the Great Attractor itself is being pulled toward something even larger and stranger. And we'll end with the question that this entire mystery forces us to confront. The question of whether our place in the universe is something we drift through quietly, or whether we are, all of us, caught in a current we never chose, heading somewhere we cannot yet name. To understand the Great Attractor, we have to go back to a time when astronomers thought they had finally figured out the universe. The early 20th century was a period of staggering revelations. In 1924, Edwin Hubble proved that the faint smudges of light astronomers had long called spiral nebulae were not clouds inside our own galaxy at all. They were galaxies in their own right. Vast, separate islands of stars, drifting through unimaginable gulfs of empty space. The universe, in a single moment, expanded from a single Milky Way to something that contained countless Milky Ways. The cosmos had grown almost beyond comprehension. And then, just 5 years later, in 1929, Hubble made an even more stunning discovery. He noticed that almost every galaxy he observed was moving away from us, and the farther away a galaxy was, the faster it was receding. This relationship, now known as Hubble's law, became the foundation of modern cosmology. It told us that the universe was not static, it was expanding. Every galaxy was rushing away from every other galaxy, like raisins in a loaf of bread rising in an oven. The implications were profound. If the universe was expanding now, it must have been smaller in the past. And if you ran the film backward far enough, everything must have once been compressed into a single point. From that idea grew what we now call the Big Bang Theory. By the middle of the 20th century, this picture had hardened into orthodoxy. The universe began roughly 13.8 billion years ago in a state of incredible density and heat. It expanded outward. It cooled. Matter clumped together into stars and galaxies, and those galaxies continued to drift apart on the rising tide of cosmic expansion. The motion of any individual galaxy could be described by a simple equation. Its speed of recession was proportional to its distance. Predictable. Orderly, almost mechanical. For decades, this picture worked beautifully. Astronomers measured the redshifts of thousands of galaxies. The data fit the model. Hubble's law held up. The universe was expanding, every galaxy was drifting outward, and the cosmos seemed, at least at the largest scales, to be a gentle and uniform thing. There were no rivers, no currents, no mysterious forces tugging structures sideways, just the steady, isotropic expansion of space itself. But there was always a wrinkle, a small one, easy to overlook. Every galaxy, in addition to its motion due to cosmic expansion, also had what astronomers called a peculiar velocity, a small extra motion, usually a few hundred kilometers per second, that wasn't explained by the expansion of space alone. This peculiar velocity was thought to be the result of local gravitational interactions, nearby galaxies tugging on each other. A galaxy might be pulled slightly toward its neighbor in a cluster. Another might be nudged by the gravitational influence of a nearby group. These motions were considered small noise on top of the dominant signal of expansion. They were interesting, but they weren't supposed to mean anything cosmic. They were local effects, local stories. The big picture remained simple. By the 1970s, astronomers had developed increasingly precise tools for measuring these motions. Radio telescopes had matured. Spectroscopy had improved. The data on galactic velocities was getting cleaner and more reliable every year. And as the data accumulated, something began to bother a small group of researchers. The peculiar velocities weren't behaving the way they were supposed to. They weren't random. They weren't pointing in scattered directions like the chaotic motions you'd expect from purely local gravitational interactions. Instead, when astronomers plotted the peculiar velocities of galaxies across large regions of the sky, a pattern started to emerge. Galaxies in our cosmic neighborhood weren't moving in random directions. They were all, to varying degrees, drifting the same way, toward the same point in the sky. The constellation of Centaurus. This was strange. This was, in fact, not supposed to happen. According to the prevailing cosmological model, on large scales, the universe should look the same in every direction. Astronomers call this principle isotropy. The universe is supposed to be smooth, uniform. There shouldn't be a preferred direction. There shouldn't be a region of sky toward which everything in our neighborhood is flowing. And yet, the data was showing exactly that. Something was wrong. Either the universe wasn't as isotropic as the theory required, or there was a massive concentration of matter somewhere in the direction of Centaurus, pulling everything toward it. A concentration so large that its gravitational influence could be felt across hundreds of millions of light years. In 1976, a group of astronomers, including Vera Rubin, Kent Ford, and Norbert Thonard, published a paper that became the opening shot in this story. They had measured the motions of galaxies relative to the cosmic microwave background, the leftover radiation from the Big Bang, which provides a kind of universal reference frame. What they found was that the Milky Way wasn't just drifting through space at random. It was moving at roughly 600 kilometers per second in a specific direction. And it wasn't only the Milky Way. The entire local group, the cluster of galaxies that includes Andromeda and dozens of smaller companions, was moving together, as one, toward a region of sky that at the time contained nothing astronomers could identify as a cause. The paper was controversial. Some astronomers questioned the data, others questioned the interpretation. The cosmic microwave background as a reference frame was still a relatively new tool. Maybe the measurements were wrong. Maybe the analysis was flawed. Maybe this apparent flow was an artifact, a statistical illusion, something that would disappear once better data came in. But the data didn't disappear. Over the following years, as more astronomers turned their instruments toward the question, the flow became more, not less, apparent. Galaxies across a vast region of the local universe were all drifting in the same direction, and the direction pointed straight into the dust-clogged plane of our own galaxy. Straight into the zone of avoidance, straight toward whatever lay hidden behind it. By the early 1980s, a small group of astronomers had become obsessed with this problem. They called themselves the Seven Samurai, after the Akira Kurosawa film. The group included Donald Lindenbell, Sandra Faber, David Burstein, Roger Davies, Alan Dressler, Roberto Turlevich, and Gary Wegner. They were brilliant, stubborn, and unwilling to accept that the strange flow they were measuring was an artifact. They spent years carefully mapping the motions of hundreds of elliptical galaxies across large regions of the sky. They were trying to build the most detailed picture yet of how galaxies were really moving in our corner of the universe. And what they found, when they finally published their results in 1988, would change cosmology forever. The Seven Samurai discovered that the streaming motion was even larger and more coherent than anyone had suspected. Galaxies across hundreds of millions of light years were all flowing toward a single point in the constellation Centaurus, at speeds far higher than any local gravitational interaction could explain. The flow was so massive, so coordinated, that the only reasonable explanation was the existence of an enormous, previously unknown concentration of mass. Something vast. Something hidden. Something pulling on the entire neighborhood. They gave it a name, almost casually, in their papers and their conference talks. They called it the Great Attractor. Nobody knew what it was. Nobody could see it. But everyone could feel it. To appreciate just how unsettling the Seven Samurai's discovery was, you have to understand what the scientific community believed about the structure of the universe before they published. In the 1970s and into the early 1980s, cosmology had a comfortable working assumption. The universe, on large scales, was supposed to be smooth. Not perfectly smooth. Astronomers knew that matter clumped into stars, stars clumped into galaxies, and galaxies clumped into clusters. But beyond a certain scale, somewhere around a few 100 million light years, the clumpiness was supposed to even out. Look at a large enough region of the cosmos, and it should appear roughly uniform. Roughly the same in every direction. This was a deep and important assumption. It was called the cosmological principle, and it wasn't just an aesthetic preference. The entire mathematical framework of modern cosmology, including the equations describing how the universe expands, depends on this assumption holding true. If the universe were lumpy on the largest scales, then the simple equations that describe cosmic expansion would break down. The Hubble law itself would lose precision. Distances would become harder to calculate. The age of the universe would become harder to determine. Cosmology, as a quantitative science, depended on the universe being more or less the same everywhere when viewed on the largest scales. So when astronomers in the early 1980s started talking about massive flows of galaxies across hundreds of millions of light years, all pointing toward a single mysterious region of sky, the reaction in much of the astronomical community was skeptical. It was almost a kind of disbelief. Surely the measurements were wrong. Surely the analysis was flawed. The universe didn't behave that way. It couldn't behave that way, not if the cosmological principle was correct. There was also a more specific reason for doubt. To produce the kind of streaming motion the Seven Samurai were reporting, you needed a concentration of mass at the destination, not a small concentration, not a single rich galaxy cluster. Something on the order of tens of thousands of times the mass of the Milky Way. That's a staggering amount of matter to assemble in one place. Astronomers had been mapping the local universe for decades. They had catalogues of galaxy clusters, lists of superclusters, surveys of the brightest objects in the sky. And there was no known structure in the direction of Centaurus that came close to having the mass required to produce the observed flow. The known galaxy clusters in that region, the Hydra cluster, the Centaurus cluster, the Parvo Indus complex, were impressive, but they weren't anywhere near big enough. Whatever was pulling on the local group with the kind of force the data implied, it was either dramatically larger than any structure catalogued, or it was hidden. The dominant view of large-scale structure in the late 1970s went something like this. Galaxies were arranged in clusters. Clusters were arranged in superclusters. Superclusters were the largest gravitationally bound structures in the universe. Beyond the supercluster scale, the cosmos thinned out and became smooth. There were no bigger players. There were no megastructures. There was nothing larger than a supercluster waiting to be discovered. This picture was reassuring. It made the universe feel manageable. It told you that once you'd catalogued the superclusters in a given region, you'd essentially mapped the gravitational landscape. You knew what was pulling on what. You could predict the motions of galaxies based on the known distribution of mass. There were no surprises waiting in the dark. The local group itself, the small cluster of galaxies containing the Milky Way, Andromeda, and their satellites, was thought to be drifting through space due to the gravitational tug of the Virgo Supercluster. Virgo, with its rich central cluster about 54 million light-years away, was the dominant gravitational influence in our cosmic neighborhood. According to the Standard Model, Virgo was supposed to be pulling us, slowly, inexorably, toward itself. And the math worked out reasonably well for a while. The motion attributable to Virgo's gravitational influence could account for some of what astronomers were measuring. But not all. There was always a residual, an extra motion that Virgo couldn't explain, a push, or rather a pull, in a direction that didn't quite match where Virgo was. For years, this discrepancy had been swept aside, attributed to measurement error or to undiscovered local structures. But by the mid-1980s, the discrepancy had grown too large to ignore. There was another piece of the puzzle that, in retrospect, was hiding in plain sight. In 1965, two researchers at Bell Labs, Arno Penzias and Robert Wilson, had accidentally discovered the cosmic microwave background, the faint glow of radiation left over from the Big Bang. This radiation filled the entire sky and was, to a very good approximation, perfectly uniform in every direction. But in the late 1970s, as instruments improved, astronomers detected a subtle imbalance. The microwave background was very slightly hotter in one direction than in the opposite direction. This is called the dipole anisotropy. The simplest explanation was that our galaxy, the Milky Way, was moving through the cosmic background. As we move toward a particular region of sky, the radiation coming from that direction is slightly blue-shifted, making it appear hotter. The radiation behind us is slightly redshifted, making it appear cooler. From the size of the temperature difference, astronomers could calculate our speed, roughly 600 kilometers per second, or about 1.3 million miles per hour. And the direction of our motion was, by an uncomfortable coincidence, almost the same direction the Seven Samurai would later identify as the source of the Great Flow. The two pieces of evidence, the dipole in the microwave background and the streaming motion of nearby galaxies, were telling the same story. Something was pulling on us, something massive, something not yet identified, and the standard model of cosmology had no obvious place for it. There was a tension building between the data and the theory. The cosmological principle insisted that the universe should be smooth on large scales. The observations were saying otherwise. By the time the Seven Samurai published their definitive paper in 1988, the tension had reached a breaking point. The standard view also rested on an assumption about how matter had been distributed in the very early universe. According to the prevailing theories of structure formation, tiny fluctuations in the density of matter in the infant cosmos had grown over billions of years into the galaxies and clusters we see today. Those fluctuations were expected to follow a particular statistical distribution. The expected outcome, after 13 billion years of gravitational evolution, was a universe full of clusters and superclusters, but with the lumpiness damping out at very large scales. There simply shouldn't have been enough time for structures larger than superclusters to assemble. The universe wasn't old enough. The math was clear. And yet, here was evidence that something hundreds of millions of light years across was acting as a coherent gravitational entity, something that, by all rights, shouldn't exist. This was the intellectual landscape into which the Great Attractor stepped, not as a quiet new addition to the catalogue, but as a contradiction, a challenge, a thing that, by the rules astronomers had agreed on, wasn't supposed to be there. The conventional wisdom said the universe was smooth at large scales. The conventional wisdom said the local gravitational landscape was understood. The conventional wisdom said nothing larger than a supercluster could exist. And then, in 1988, a small group of astronomers stood up at conferences and explained with data that the conventional wisdom was wrong. The first cracks didn't arrive all at once. They came slowly, accumulating over a decade of measurements that didn't quite add up. And the people who noticed them weren't trying to overturn cosmology. They were trying to do something much more mundane. They were trying to measure distances. It sounds simple. It is not. Measuring the distance to a galaxy is one of the hardest problems in observational astronomy. You can't send a tape measure to Centaurus. You can't bounce a radar signal off Andromeda and time the return. The light from these objects takes millions of years to reach us. The only tools astronomers have are indirect ones: brightness measurements, spectral analysis, statistical correlations between observable properties of galaxies, and every method comes with uncertainty. In the late 1970s and early 1980s, a new method emerged that promised to revolutionize the field. It was based on a relationship discovered by two astronomers, R. Brent Tully and J. Richard Fisher in 1977. They had noticed that the rotation speed of a spiral galaxy was tightly correlated with its intrinsic luminosity. The faster a galaxy spins, the brighter it actually is. If you could measure how fast a galaxy was rotating, you could calculate how much light it must really be emitting. And if you knew how much light it really emitted and how much light you actually saw from Earth, you could calculate how far away it must be. This is called the Tully-Fisher relation. For elliptical galaxies, which don't rotate the same way, a similar relationship was developed using the spread of stellar velocities inside them. It was called the Faber-Jackson relation, and later refined into something called the fundamental plane. These new tools were transformative. They gave astronomers, for the first time, a way to estimate the distance to a galaxy independently of its redshift. This was crucial. Because if you knew a galaxy's distance from one method, and its redshift from another, you could calculate how much of the galaxy's motion was due to cosmic expansion, and how much was due to peculiar velocity. You could separate the steady outward drift caused by the expansion of space from the local, gravitationally induced motions caused by nearby masses. You could, for the first time, actually map the gravitational landscape of the nearby universe. And when astronomers started doing this, the map looked wrong. The first hints came from a researcher named Mark Aronson, working with John Huckra and Jeremy Mould in the late 1970s. They had been using infrared observations to apply the Tully-Fisher method to spiral galaxies in nearby clusters. Their results showed something puzzling. The peculiar velocities they were measuring didn't form a random pattern. There was structure in the noise, a coherence that shouldn't have been there. Aronson and his colleagues didn't immediately announce that they had found a new cosmic structure. They were careful. They suspected systematic errors. They worried about biases in their sample. They tested their methods against the predictions of the standard cosmological model, and they found tensions, but tensions could come from many sources. The data was suggestive, but not yet conclusive. Aronson would never see the full story emerge. He was killed in a tragic accident at Kitt Peak Observatory in 1987, struck by the rotating dome of the telescope he had used to make so many of his observations. He was 36 years old. While Aronson was working, other astronomers were also noticing strange things. In 1976, Vera Rubin, Kent Ford, and Norbert Thonard published a paper that looked at the motions of distant galaxies as a way to test whether the universe was truly isotropic. They expected to find no significant deviation from uniformity. What they found instead was a hint of a large-scale flow. The Milky Way appeared to be moving relative to a sample of distant galaxies at a speed that was hard to explain. The paper, often called the Rubin-Ford effect, was met with skepticism. It was based on a small sample. The statistical analysis was challenged. Some astronomers thought the effect was real. Others thought it was an artifact of the way galaxies had been selected for the study. The debate dragged on for years without resolution, but the seed had been planted. The idea that the local universe might be moving as a coherent unit relative to the more distant cosmos refused to die quietly. Then came the cosmic microwave background measurements. Throughout the late 1970s, increasingly precise observations of the leftover radiation from the Big Bang had revealed the dipole anisotropy. The radiation was slightly hotter in one direction than the other. The interpretation was straightforward. Our galaxy was moving through the cosmic background, but the direction of the motion and its speed didn't match what astronomers expected from the local gravitational landscape. If the Milky Way were being pulled only by the Virgo Supercluster, our motion should have been smaller and pointed differently. The microwave background was telling us we were moving faster than the Virgo model allowed, and in a direction that didn't quite match Virgo's location. The discrepancy was small but persistent. It refused to go away no matter how the data was reanalyzed. By the early 1980s, 3 separate pieces of evidence had emerged. The Rubin-Ford effect hinted at large-scale flows. The Tully-Fisher measurements showed coherent, peculiar velocities. The microwave background dipole indicated a Milky Way motion that the local gravitational landscape couldn't fully explain. Individually, each piece of evidence was contested. Each had its critics. Each could be dismissed if you tried hard enough, but together they were pointing toward something. A pattern was emerging. And the pattern said that the nearby universe was not behaving the way the standard cosmological model predicted. There was an intellectual difficulty here that went beyond the data itself. Astronomers are trained to be conservative. They know that history is littered with claims of cosmic anomalies that turned out to be mistakes. The discovery of canals on Mars, the supposed detection of a planet inside Mercury's orbit, the countless claimed observations of objects that, on closer inspection, were measurement artifacts. To stand up and say that the standard model of cosmology was missing something fundamental was not a casual thing to do. It required overcoming a deep institutional reluctance. It required being willing to be wrong in public. And the people who first began to take the anomalies seriously were aware of this. They moved carefully. They published cautiously. They left themselves room to retreat, but the data kept accumulating. By the mid-1980s, several groups around the world were measuring galaxy motions with increasing precision. Independent teams using different methods were converging on the same conclusion. There was a flow. It was real. It pointed in a specific direction, and the magnitude of it implied a gravitational source of enormous mass, somewhere out there, somewhere we couldn't see clearly. The combined weight of the evidence was becoming impossible to dismiss as systematic error or statistical fluke. Something was happening in the local universe, something the standard model hadn't predicted. The cracks in conventional wisdom had become fissures. What no one had yet done was the comprehensive, painstaking work needed to turn these scattered hints into a definitive map, to measure the motions of hundreds of galaxies across large regions of sky, to calibrate the distance methods with extraordinary care, to map the flow in 3 dimensions and pinpoint where it was leading. That was the work that the 7 samurai had set themselves to do, and it would take them years to complete it. To pin down something invisible, you need instruments that can see what the eye cannot. The story of how astronomers eventually mapped the Great Attractor is, in many ways, the story of the tools they built and the techniques they refined. Because the obstacle wasn't conceptual. By the mid-1980s, most astronomers were willing to accept, at least in principle, that something unusual might be happening in the local universe. The obstacle was practical. How do you measure the motion of hundreds of thousands of galaxies with enough precision to detect a flow of a few hundred kilometers per second, when the galaxies themselves are millions of light years away, and their light is contaminated by every kind of cosmic and atmospheric noise imaginable? The answer required a combination of 3 different kinds of technology, each pushing against the limits of what was possible at the time. The first was spectroscopy. To measure how fast a galaxy is moving toward or away from us, you have to analyze its light. When a galaxy moves away from Earth, its light is stretched to longer wavelengths, shifted toward the red end of the spectrum. When it moves toward us, the wavelengths are compressed, shifted toward the blue. The amount of shift tells you the velocity along our line of sight. This effect, called the Doppler shift, is the same principle that makes an ambulance siren sound higher as it approaches and lower as it recedes. Astronomers have been measuring redshifts since the early 20th century. But to detect the kind of subtle flows the 7 samurai were chasing, you needed extraordinarily precise spectra of hundreds of galaxies. The instruments of the 1970s, with their photographic plates and slow data collection, simply weren't fast enough. What changed everything was the arrival of digital detectors. Charge-coupled devices, or CCDs, were originally developed for military and industrial applications. By the late 1970s, they were being adapted for astronomy. A CCD could collect light far more efficiently than a photographic plate, capturing faint objects in a fraction of the exposure time, and the data came out in a form that could be analyzed by computer rather than by eye. The improvement was revolutionary. Surveys that would have taken decades with older technology could now be completed in a few years. The second piece of the puzzle was a reliable way to estimate distances to galaxies independently of their redshifts. This is where the Tully-Fisher and Faber-Jackson relations became indispensable. For spiral galaxies, astronomers could measure the rotation speed of the galactic disk by looking at how the spectral lines from gas at the galaxy's edges were broadened. The broader the spread, the faster the rotation. The faster the rotation, the more luminous the galaxy must intrinsically be. Compare that intrinsic luminosity to how bright the galaxy actually appears from Earth, and you could calculate a distance. For elliptical galaxies, the equivalent was the fundamental plane, a relationship between a galaxy's size, its surface brightness, and the velocity dispersion of its stars. The mathematics behind these relations is intricate, but the basic idea is elegant. Find a property of a galaxy that is correlated with its true brightness. Measure that property. Use the correlation to predict the true brightness. Compare to the observed brightness. Distance falls out of the calculation. The Seven Samurai relied heavily on the elliptical galaxy version, the precursor to the fundamental plane, because elliptical galaxies are bright, abundant in dense regions of the universe, and reasonably well-behaved targets for the kind of careful work they wanted to do. The third element was radio astronomy. Radio telescopes had been operating since the 1930s, but the technology had matured dramatically in the post-war decades. By the 1980s, astronomers had powerful instruments capable of detecting the 21-centimeter emission line of neutral hydrogen, a specific wavelength of radio waves emitted by hydrogen atoms throughout the universe. This wavelength is critical because nearly every galaxy contains vast clouds of hydrogen gas, and the 21-centimeter line can be detected even through significant amounts of intervening dust. Optical telescopes are blind to galaxies hidden behind the dust of our own Milky Way. Radio telescopes, looking at much longer wavelengths, are not. This would prove essential in the years to come, when astronomers began trying to peer into the zone of avoidance directly. But even before that effort began in earnest, radio measurements were already providing critical data on the rotation speeds of spiral galaxies, allowing the Tully-Fisher method to be applied with higher precision than optical observations alone could achieve. The Seven Samurais project was in some ways a synthesis of all three technologies. They selected a sample of about 400 elliptical galaxies distributed across the sky. They used optical telescopes equipped with the new CCD detectors to obtain precise photometric measurements of each galaxy's size and surface brightness. They used spectrographs to measure the velocity dispersions of stars within each galaxy. And they used the resulting data, processed through the relations they had refined, to calculate distances. Once they had distances, they could compare those distances to redshifts, and the difference revealed each galaxy's peculiar velocity. Multiply this process by hundreds of galaxies, plot the results across the sky, and a pattern of motion emerged. This was the technique that finally turned anecdotal hints of a large-scale flow into a definitive map. There was a parallel effort that would later become essential, and it deserves attention here even though its biggest contributions came after the initial discovery. Throughout the 1980s and into the 1990s, astronomers began conducting systematic radio surveys of the zone of avoidance. Optical surveys had always avoided the galactic plane because of the dust, leaving a gap in the cosmic map that ran like a thick band across our view of the universe. But radio surveys could see right through that dust. Projects using telescopes like the Parkes Observatory in Australia and the Effelsberg Radio Telescope in Germany began the slow, patient work of cataloging galaxies hidden behind our own galactic disk. The 21-centimeter line gave away their presence, and with each new detection, the blind spot in our cosmic map shrank. The zone of avoidance, it turned out, was not empty. It was full of galaxies, including, as later surveys would show, some of the most massive structures relevant to the Great Attractor itself. X-ray astronomy added another layer. Galaxy clusters contain not just galaxies, but enormous reservoirs of hot, diffuse gas trapped in their gravitational wells. This gas is so hot, often tens of millions of degrees, that it emits X-rays. From Earth's atmosphere, X-rays from space are blocked entirely, which is why X-ray astronomy requires telescopes in orbit. The launch of satellites like ROSAT in 1990 gave astronomers a new way to detect massive clusters, even ones hidden behind galactic dust. X-rays could pierce the obscuration that defeated optical surveys, and a bright X-ray source in the Zone of Avoidance was a strong hint that a major galaxy cluster lay hidden there. ROSAT and later missions would play a key role in confirming the existence of specific structures behind the dust that contributed to the Great Attractor's gravitational pull. What made all of this work possible, ultimately, was the patience to combine many imperfect tools into a coherent picture. No single instrument could solve the problem. Optical telescopes were blocked by dust. Radio telescopes lacked the precision for some measurements. X-ray telescopes had to be flown above the atmosphere. Distance estimates carried significant uncertainties. Spectroscopy required hours of observation per galaxy. But by stitching together data from all these sources, by cross-checking results, by refining the calibrations year after year, astronomers slowly built a map of motion that no individual technology could have produced alone. The Great Attractor would not have been discovered with any single instrument. It was discovered instead by an entire generation of astronomers learning, painfully and gradually, how to see what had always been hidden. The Seven Samurai's definitive paper landed in 1988, and it changed the landscape of cosmology in a single stroke. The paper was titled Spectroscopy and Photometry of Elliptical Galaxies, V galaxies streaming toward the new supergalactic center. The dry, technical title concealed a result that was, for the field, almost incendiary. The 7 authors, working together over years of careful observation, had measured the distances and peculiar velocities of nearly 400 elliptical galaxies spread across the sky. When they plotted the motions, the pattern was unmistakable. A vast region of the local universe, including our own Milky Way, the entire local group, the Virgo Supercluster, and structures beyond, was flowing as one. All of it drifting together at speeds of several hundred kilometers per second toward a single point in the southern sky. The convergence point lay in the constellation Centaurus, somewhere behind the dust of our own galactic plane. The flow was coherent over a region at least 200 million light-years across. The gravitational source required to produce it had to contain a mass of roughly 50,000 times that of the Milky Way, tens of quadrillions of solar masses, hidden, invisible, but unmistakably there. The scientific reaction was a mixture of fascination, skepticism, and a particular kind of unease. Fascination, because if the result was correct, it meant the universe contained structures far larger and more massive than anyone had suspected. Skepticism, because the result depended on distance measurements that had inherent uncertainties, and an error in the calibration of the fundamental plane could in principle produce a spurious flow. And unease, because if the universe really did contain a structure on the scale the 7 samurai were claiming, the cosmological principle was in serious trouble. The smooth, isotropic universe that cosmologists had built their models on was beginning to look like an oversimplification. Some astronomers immediately accepted the result. Others demanded more data. A vigorous and sometimes heated debate erupted at conferences and in journals throughout the late 1980s and into the 1990s. What gave the 7 samurai result staying power against the resistance it initially encountered was that it didn't stand alone. Other groups, using independent methods, were beginning to report similar findings. A team led by Todd Lauer and Mark Postman, working with brightest cluster galaxies as distance indicators, had been measuring large-scale flows and finding patterns consistent with the existence of a major mass concentration. Independent work using infrared galaxy surveys, particularly the IRAS satellite catalog, was mapping the distribution of galaxies in the local universe and finding mass concentrations that, by themselves, could not fully account for the observed flow. There was a deficit. Even when astronomers added up all the known galaxy clusters and superclusters in our cosmic neighborhood, the predicted gravitational pull fell short of what was being measured. The flow was real. The known structures were not enough to produce it. The conclusion was almost forced. Something massive and previously uncatalogued had to exist in the direction the galaxies were flowing. The name, Great Attractor, had been used informally for a few years before the 1988 paper, but it now entered the scientific mainstream. Donald Lindenbell, one of the 7 samurai, had a particular fondness for it. The name captured something important about what they had found. The thing wasn't a galaxy, it wasn't a cluster, it wasn't even, strictly speaking, a confirmed object. It was, first and foremost, a region of space defined by its gravitational influence, a great attractor, a pull, a direction in the cosmic compass that everything in our neighborhood was following. The name stuck because no better one existed. We didn't know what it was, we only knew what it did. The follow-up work in the late 1980s and early 1990s tried to characterize the Great Attractor in more detail. Where exactly was it? How massive was it? What kind of structure could plausibly contain that much mass? The best estimates placed it at a distance of roughly 150 to 250 million light-years from Earth, in the general direction of the constellations Centaurus, Hydra, and Norma. The mass estimates varied depending on assumptions, but most calculations converged on something like 10 to the 16th solar masses, equivalent to a supercluster many times larger than anything catalogued in the optical surveys. A supercluster of superclusters, in some descriptions. A gravitational anchor for everything within hundreds of millions of light-years of our galaxy. But here is where the story became deeply frustrating. The Great Attractor lay almost directly behind the densest part of the Milky Way's disk, in the Zone of Avoidance. Optical telescopes, no matter how powerful, simply could not see through the wall of dust and stars our own galaxy threw across that region of sky. The Hubble Space Telescope, launched in 1990, was useless for this purpose. So was the most ambitious ground-based optical observatory. The same accident of geometry that had hidden the Great Attractor from astronomers for so long continued to hide it even after they knew where to look. It was as if the universe had played a cruel joke. The largest gravitational structure in our cosmic neighborhood happened to lie behind the one part of the sky that our instruments couldn't penetrate. This forced astronomers to develop new strategies. If optical telescopes couldn't see the Great Attractor directly, then they would have to be clever. They would have to use other parts of the electromagnetic spectrum that could pierce the galactic dust. Radio observations, particularly at the 21-centimeter line of neutral hydrogen, became essential. Infrared surveys, less affected by dust than visible light, began to reveal galaxies hidden behind the Milky Way's curtain. X-ray observations, conducted from orbit, could detect the hot gas trapped in massive galaxy clusters even when the clusters themselves were obscured at visible wavelengths. The 1990s would become a decade of slow, painstaking work, piecing together evidence from multiple wavelengths, gradually filling in the dark band of the Zone of Avoidance with newly discovered galaxies and clusters. What emerged from this effort was both reassuring and unsettling. On the reassuring side, astronomers did begin to find massive structures behind the dust. The Norma cluster, also known as Able 3627, was identified as a major galaxy cluster lying very close to the calculated center of the Great Attractor. It was rich, massive, and clearly contributed to the gravitational pull on our region of the universe. Other clusters and concentrations of galaxies in the same general area added to the picture. The Great Attractor was beginning to acquire actual identified components. It was not entirely a ghost. It had pieces astronomers could point to. But on the unsettling side, even when all the newly discovered structures behind the Zone of Avoidance were added up, they still didn't quite account for all of the mass needed to produce the observed flow. The Norma cluster was massive, but not massive enough by itself. The surrounding structures helped, but the sum was still less than the gravitational signal demanded. This was the situation by the mid-1990s. The Great Attractor was real. Pieces of it were being identified. The discovery had appended the assumption that the universe was smooth on hundreds of millions of light years and had revealed structures larger than anyone had thought possible. And yet, the full story remained out of reach. There was more out there. Something even larger, even more distant, was still hiding. The flow that the Seven Samurai had measured was just the first hint of a much grander structure that astronomers were only beginning to glimpse. The Great Attractor, it would turn out, was not the end of the story. It was the doorway into a deeper mystery. The first hint that the Great Attractor was not the whole answer came from a strange inconsistency in the data. Throughout the early 1990s, as astronomers continued to refine their measurements of galaxy motions across larger and larger volumes of the universe, they noticed something peculiar. If the Great Attractor were truly the only significant gravitational anomaly in our cosmic neighborhood, then as you measured galaxies on the far side of it, beyond the calculated center of mass, those galaxies should be flowing back toward the Great Attractor from the opposite direction. Imagine a marble rolling toward a deep gravity well. On one side, marbles approach from one direction. On the other side, marbles approach from the opposite direction. If you map all the marbles, you should see them converging from every direction onto the central pit. The Great Attractor, if it were a simple, isolated gravitational source, should produce exactly this kind of converging flow pattern. But that wasn't what astronomers were finding. When they measured galaxies on what should have been the far side of the Great Attractor, those galaxies weren't flowing back toward it. They were continuing to flow in the same direction as our own galaxy, as if the Great Attractor itself were being pulled along with us, as if both we and the Great Attractor were riding on the same cosmic current, headed somewhere else entirely. The implication was startling. The Great Attractor wasn't the final destination. It was just a way station. A massive, gravitationally significant structure in its own right, yes, but itself caught in the gravitational grip of something larger, something farther away, something we had not yet identified at all. For most of the 1990s, this finding remained controversial. The data was suggestive, but not conclusive. Measuring galaxy motions at distances of 300, 400, even 500 million light-years from Earth was right at the edge of what existing technology could achieve. The error bars were enormous. The possibility that the apparent continuation of flow beyond the Great Attractor was a measurement artifact could not be ruled out. Some astronomers argued that with better data, the picture would resolve into a simpler one, with the Great Attractor as the true center. Others argued that the data was already pointing towards something more complex and that the simpler picture was wishful thinking. The debate played out across journal papers and conference talks throughout the decade. New galaxy surveys were planned. New instruments were proposed. The community waited for clarity. While the debate continued, astronomers were also making progress on the parallel question of what, exactly, the Great Attractor was made of. Radio and infrared surveys of the Zone of Avoidance continued to reveal hidden structures. By the late 1990s, a clearer picture was emerging. The Great Attractor was not a single object. It was not a single galaxy cluster, no matter how massive. It was, instead, a complex region of space containing multiple superclusters and massive clusters, all linked together by the cosmic web. At its core lay the Norma cluster, that massive but previously obscured concentration of galaxies. Around it stretched a broader structure that astronomers began calling the Centaurus Hydra supercluster, or sometimes the Centaurus Wall, a sprawling assembly of galaxies spanning hundreds of millions of light-years. The Great Attractor, in other words, was real, but it was diffuse. It was a region, a neighborhood, a vast architectural feature of the cosmic web rather than a single point of mass. This refined understanding made the persistence of flow beyond the Great Attractor even more puzzling. If the Great Attractor was already a sprawling supercluster complex containing tens of quadrillions of solar masses, what could possibly be massive enough to pull all of that along, while also pulling our entire local universe in the same direction? The numbers strained credibility. Whatever was behind the Great Attractor would have to be larger still, more massive still. And it would have to be far enough away that it had not been obvious in the original 1988 measurements, because those measurements had been focused on a smaller volume of space. The breakthrough came in the early 2000s, as new generations of galaxy redshift surveys finally pushed deep enough into the universe to map the larger-scale flow with reasonable precision. The 2DF Galaxy Redshift Survey, conducted from the Anglo-Australian Telescope in the late 1990s and early 2000s, mapped the redshifts of roughly 230,000 galaxies across large regions of the sky. The Sloan Digital Sky Survey, beginning in 2000, would eventually catalogue millions more. With these enormous datasets, astronomers could begin to construct three-dimensional maps of the local universe out to billions of light years. And what those maps revealed was that the Great Attractor was not the dominant feature of our cosmic neighborhood after all. It was a major feature, certainly, but beyond it, much farther away, lay something larger. This something was eventually given a name. The Shapley Supercluster, also called the Shapley concentration, had actually been known to astronomers for decades. Harlow Shapley, the American astronomer for whom it is named, had identified an apparent overdensity of galaxies in the constellation Centaurus back in the 1930s. At the time, no one understood what the concentration meant or whether it was gravitationally significant on cosmic scales. For most of the 20th century, it was simply catalogued as one of many large galaxy concentrations in the local universe, an oddity of distribution without obvious dynamical importance. But as the flow data from the late 1990s and early 2000s came in, astronomers began to realize that the Shapley Supercluster was in the line of fire. It lay almost exactly in the direction the galaxies were flowing, but at a distance of roughly 650 million light-years from Earth, well beyond the Great Attractor's 200 million light-year distance. And its mass was extraordinary. The Shapley Supercluster contained at least 20 major galaxy clusters and many smaller groupings, with a total mass estimated at more than 10 to the 16th solar masses, comparable to or even greater than the Great Attractor itself. The implication slowly became clear. The Shapley Supercluster was contributing significantly to the gravitational pull on our local universe. The Great Attractor was real and important, but a substantial portion of the flow originally attributed to it was actually being driven by the much more distant, much more massive Shapley structure. Some estimates suggested that as much as half of our peculiar velocity might be due to the pull of Shapley, with the Great Attractor accounting for the rest. The picture was no longer one of a single gravitational anomaly. It was a layered picture, with structures upon structures, each contributing to the flow, each playing a part in determining where the galaxies of our cosmic neighborhood were headed. The Great Attractor itself was not the deepest layer. It was a feature in a much grander gravitational landscape. The discovery that the Great Attractor was being pulled by something larger was, in some ways, the moment when cosmology had to admit that the local universe was even less smooth, less uniform, less manageable than the most pessimistic interpretations of the 1988 data had suggested. The cosmological principle, the assumption that the universe was the same in every direction on the largest scales, was looking shakier than ever. There were structures here. There were patterns. There were currents. The cosmos was not a featureless ocean. It was a river system with tributaries and main channels and powerful underlying flows. And the deeper astronomers looked, the more they realized that the structures they were finding might extend even further than the Shapley Supercluster. The story was not over. The pattern was still emerging. By the mid-2000s, the picture had grown more intricate than anyone in the Seven Samurai era could have imagined. The Great Attractor was real but partial. The Shapley Supercluster was contributing significantly to the pull. And yet, as astronomers extended their measurements deeper, still into the universe, they began to notice that even the combined gravity of these two structures didn't quite account for everything. There were residual motions that pointed beyond Shapley, hints of flow patterns extending across regions of space so vast that the human mind has no analogy for them. The pattern was not just a story about two structures pulling on us. It was a story about a hierarchy, layers within layers, currents within currents, and the realization that began to dawn slowly was that what we were seeing was not a collection of isolated gravitational anomalies. It was the architecture of something much larger, something with its own shape, its own boundaries, its own coherent identity. We were starting to glimpse the contours of a cosmic structure that no one had ever catalogued before. The breakthrough came from a research group led by R. Brent Tully, the same astronomer who had co-developed the Tully-Fisher relation decades earlier. Tully had spent his career mapping the local universe with increasing precision, and by the 2010s, he and his collaborators had assembled a database of galaxy distances and velocities so detailed that they could finally do something no one had ever done before. They could map not just the positions of galaxies, but the gravitational flow lines connecting them. Imagine standing on a hillside and watching water flow downhill. Each drop follows the local slope. If you trace the paths of enough drops, you can map the watershed. You can identify the basins where the water collects. You can see, on the ground, where one valley ends and the next begins. Tully and his team realized they could do the same thing with galaxies. The peculiar velocities of galaxies trace the slope of the cosmic gravitational landscape. By following those velocity vectors, by mapping where the galaxies were flowing, they could identify the basins of attraction in the local universe. They could draw, for the first time, the actual boundaries of our gravitational neighborhood. The result, published in 2014 in the journal Nature, was a paper that quietly reframed our place in the cosmos. Tully and his colleagues had identified a single, coherent structure containing the Milky Way, the entire local group, the Virgo Supercluster, the Great Attractor, and tens of thousands of other galaxies. All of them bound together not by being gravitationally locked into a single cluster, but by all flowing toward the same set of gravitational basins. The structure was enormous, roughly 500 million light-years across, containing the mass of perhaps 100 quadrillion suns. The team gave it a name, drawing from the Hawaiian language out of respect for the observatories on Mauna Kea that had contributed so much data to the project. They called it Laniakea. The word means immeasurable heaven. It was a fitting name for something so large, so unprecedented, that the term supercluster no longer felt adequate. Laniakea was not just a bigger supercluster, it was a new category of structure. A supercluster of superclusters, defined not by the traditional criterion of gravitational binding. Since at scales this large, the expansion of the universe prevents anything from being fully bound, but by the watershed of cosmic flow. Everything inside Laniakea is flowing inward. Everything outside it is flowing toward other distant basins. And at the very heart of Laniakea, at the deepest point of the gravitational basin, lies the Great Attractor. The structure that had puzzled astronomers for decades was now revealed to be the centerpiece of a much larger architectural feature. It was, in a sense, the core of our cosmic home. The thing all of us, every star and planet in tens of thousands of galaxies, are slowly falling toward as we ride the current of Laniakea's interior flow. This was a profound shift in perspective. For most of human history, we had thought of our place in the universe in terms of nested structures of increasing size. Earth, solar system, Milky Way, local group, Virgo Supercluster, each containing the one before, each well-defined, each known. Laniakea added a new level to that hierarchy, but it did so by redefining what a level meant. Our cosmic address was no longer just a list of containers. It was a description of where we sat in a flowing landscape, defined by the direction we were being pulled rather than by clear gravitational boundaries. We were not just citizens of a galaxy or a supercluster. We were inhabitants of a vast gravitational basin, with the Great Attractor as its drain. The discovery of Laniakea also began to clarify why the Shapley supercluster had become so important to the story. Shapley sits not within Laniakea, but in an adjacent gravitational basin, just across the cosmic watershed. From Laniakea's perspective, Shapley is on the outside, in its own neighborhood, with its own gravitational dynamics. But Shapley is so massive that its gravitational influence extends across the boundary. It pulls on Laniakea as a whole. Our entire home structure, all 100 quadrillion solar masses of it, is being tugged in the direction of Shapley. Not because Shapley is part of our basin, but because it is so enormous that even from across the divide, it exerts an unmistakable pull. The flow we feel is the flow of Laniakea itself, drifting toward a neighbor more massive than it. There was another piece of the puzzle that Tully and his colleagues uncovered. Just as Laniakea has its core in the Great Attractor, neighboring structures have their own cores. Mapping the flow patterns revealed several other major basins of attraction in our region of the universe. The Perseus-Pisces supercluster, which lies in a different direction from Earth, defines a basin of comparable size to Laniakea, but with its own internal dynamics. The Coma supercluster anchors another basin. The Hercules Supercluster, yet another. The local universe, on the largest scales, is divided into these massive flow basins, separated by underdense regions called voids, where the cosmic web thins out into near emptiness. The pattern is not random. It is structured. The universe, at the scales of hundreds of millions of light years, is organized into a complex topography of basins and ridges, like a continent seen from orbit, with rivers of galaxies flowing through its valleys. The implications of this picture were both clarifying and unsettling. Clarifying, because for the first time, we had a coherent map of the gravitational landscape of the local universe. We knew where we were in terms of the larger flow. We knew which basin we belonged to. We knew where the boundaries lay. Unsettling, because the picture revealed that the cosmological principle, the foundational assumption that the universe was the same in every direction, was holding up worse than ever. Structures, hundreds of millions of light years across, were behaving as coherent dynamical entities. The cosmos was not a smooth ocean. It was a landscape, and we were inhabitants of one of its valleys, being carried along by currents we did not choose and had only begun to understand. The Great Attractor was no longer a mystery hovering at the edge of our maps. It was now, definitively, the heart of our home. And our home, in turn, was being pulled by something farther away still. The discovery of Laniakea answered some questions and immediately raised harder ones. We now knew the architecture of our local gravitational basin. We knew where its center lay. We knew which neighboring basin was pulling us. But the more carefully astronomers looked, the more they began to notice things that didn't fit. Anomalies, inconsistencies, pieces of the puzzle that refused to lock into place. By the late 2010s, a quiet sense was building in the community that even the Laniakea picture, comprehensive as it seemed, was not the whole story. There was something paradoxical about the flow data. Something that the existing structures, the Great Attractor and Shapley, and even the broader cosmic web, could not fully explain. And the more astronomers probed, the stranger the paradox became. The first anomaly involved the magnitude of the flow itself. When astronomers carefully measured the bulk motion of galaxies in our region of the universe, the speeds they detected were systematically higher than what the standard cosmological model predicted. The standard model, called lambda-CDM, makes specific predictions about how much peculiar velocity galaxies should have at various scales. It accounts for the influence of dark matter, the slow growth of cosmic structure, the expansion of space, and the gravitational pull of known concentrations of mass. When you plug in all the catalogued structures within a few 100 million light years of Earth, you get a prediction for the typical peculiar velocity of galaxies in our neighborhood. Compare that prediction to the actual measurements, and you find a discrepancy. The galaxies are moving faster than they should be, not by an enormous amount, but by enough to make the result statistically significant and by enough that it cannot be easily dismissed as measurement error. This is sometimes called the dark flow problem, although the term itself is contested and has been applied to several different anomalies over the years. The basic puzzle is that the gravitational sources we have identified, even with Laniakea mapped out and Shapley accounted for, and all the other known basins of attraction included, are not quite sufficient to explain the speeds at which the galaxies are actually moving. The motion is too fast. Something is missing. Either our census of the local universe is incomplete, with major structures still hidden behind the zone of avoidance or in other obscured regions of the sky, or the underlying physics needs adjustment, or there is some other gravitational influence at work that the current models do not include. None of these possibilities is comfortable. The second anomaly was even stranger. In 2008, a research team led by Alexander Kashlinsky published an analysis claiming to detect coherent motion of galaxy clusters at distances of up to several billion light years. The paper argued that the motion was not consistent with the gravitational pull of any known local structures. Instead, it pointed beyond the observable universe, beyond what we can see, toward something so far away that, by the standard cosmological model, it shouldn't be able to influence us at all. The claim was controversial from the beginning. Other groups attempted to replicate the result and reached different conclusions. The interpretation was attacked on statistical grounds. The data was reanalyzed, debated, and disputed. As of the early 2020s, the existence of this kind of large-scale coherent flow at very large distances remained an open and contested question. Some researchers consider it a real anomaly. Others consider it a measurement artifact. The community has not yet reached consensus, but the existence of the debate itself was telling. If there had been any clean, simple way to resolve the question, it would have been resolved by now. The fact that careful researchers using sophisticated methods could disagree about whether or not coherent flows extended across billions of light years suggested that we were operating right at the limits of what our current data could tell us. Whatever lay beyond the standard picture, if anything did, was hovering just at the edge of detectability, visible to some instruments and not to others, apparent in some analyses and not in others. The cosmic landscape, it seemed, was even more textured and complicated at the largest scales than the Laniakea map had suggested. There was a third paradox, one that struck closer to the foundations of cosmology itself. Throughout the 2010s and into the 2020s, astronomers had been measuring the rate at which the universe is expanding using two very different methods. One method, based on observations of the cosmic microwave background and the conditions of the early universe, gave one value for the Hubble constant, the parameter that describes the expansion rate. Another method, based on observations of nearby galaxies and their distances measured through Cepheid variable stars and supernovae, gave a different value. The two measurements disagreed by more than the error bars allowed. This is now called the Hubble tension, and it has become one of the most pressing problems in modern cosmology. The disagreement is not enormous, just a few percent, but it is statistically significant, and it has resisted all attempts at resolution. Some cosmologists have wondered whether the Hubble tension might be related to the local flow anomalies. If our region of the universe is part of a particularly large gravitational basin, our local measurements of expansion might be biased in subtle ways. The flow itself, if it extends further than we currently realize, might be distorting our view of the cosmic expansion rate. This is speculative, but it points to a deeper unease in the field. There may be something fundamental we are missing about the structure of our universe. And then there is the most paradoxical element of all. The Great Attractor, even now, even after decades of careful observation, has never been seen directly in optical light. Every other major structure in our cosmic neighborhood has been imaged at multiple wavelengths and characterized in detail. Virgo, Coma, Perseus Pisces, even the distant Shapley concentration, all have been studied with optical telescopes that have produced beautiful, detailed maps of their constituent galaxies. The Great Attractor remains the great exception. Its core lies hidden behind the densest part of the Milky Way's disk, in the Zone of Avoidance, and the optical view is permanently obscured. We can see its periphery. We can study the galaxies that lie just outside the dust band. We have detected its massive components through radio and infrared and X-ray observations. But the heart of it, the Norma cluster and its surroundings, remains visually elusive. There is something almost mythological about this. The single most important gravitational feature of our local universe, the structure pulling our entire home toward it, is the one structure we are physically unable to look at directly. The cosmos has placed our home in the worst possible viewing position for understanding our own destination. This obscuration is not merely an inconvenience. It introduces real uncertainties into our measurements. Estimates of the Great Attractor's total mass still vary by a factor of 2 or more depending on which combination of indirect observations you trust. Maps of the galaxies behind the dust band remain incomplete. New galaxies are still being discovered in the Zone of Avoidance every year, each one a piece of the puzzle that had been hidden in plain sight. Until we have a complete inventory of what lies behind the dust, our picture of the Great Attractor will remain provisional. And the anomalies in the flow data, the motions that don't quite add up, may be telling us that the inventory is more incomplete than we realize. There may be major structures still hidden, still uncatalogued, still pulling on us from behind the curtain we cannot pierce. Now we arrive at the moment that changes the entire story. Because in 2017, R. Brent Tully and his collaborators published another paper. The Laniakea paper had given us a name for our home. This new paper gave us something more disturbing. It revealed that the flow we had been measuring all these decades, the flow toward the Great Attractor, the flow toward Shapley, the flow that defined the inner currents of Laniakea, was only half of the picture. The other half had been completely invisible to us, not hidden by dust, not obscured by our own galaxy, hidden in a way that was, in some ways, even stranger. It had been hidden by the absence of matter, by the emptiness of space, by a vast region of the universe so devoid of galaxies that no one had thought to look there for an explanation. The paper was titled The Dipole Repeller, and it reframed everything we thought we knew about our motion through the cosmos. The argument was elegant once you saw it. Gravity, traditionally, is described as a force of attraction. Massive objects pull on each other. The Great Attractor pulls us toward it. The Shapley Supercluster pulls Laniakea toward it. The cosmic web is a tapestry of gravitational basins, all defined by where matter has clumped together. But there is another way to think about gravitational dynamics. Imagine a flat plane. Now imagine that someone digs a pit in the middle of it. A marble placed on the plane will roll toward the pit. From the marble's perspective, it is being pulled into the depression. But you can describe the same motion in a different way. Compared to the marble, the rest of the plane is higher up. The marble is moving away from the higher ground. It is being repelled from the elevated edges of the plane, even though no force is actively pushing it. The math is identical. The motion is the same, but the perspective is different. Tully and his team realized that the cosmic flow could be analyzed the same way. Yes, we are being pulled toward the Great Attractor and Shapley, but we are also being pushed away from regions of the universe where there is less matter than average. These regions, called cosmic voids, are vast tracts of nearly empty space, hundreds of millions of light years across, where galaxies are rare and the cosmic web has thinned almost to nothing. From a gravitational perspective, a void acts like a hill. Matter on one side of the void is pulled by everything around it except by the void itself, because there is less mass there than expected. The net effect is that the void appears to push surrounding matter away from it. Not because there is any actual repulsive force, but because the lack of gravity on the void side is overwhelmed by the presence of gravity on the opposite side. Move into the void, and you find yourself being pulled out of it by the surrounding masses. From outside, the same dynamic looks like the void is shoving matter away. When Tully and his team applied this analysis to the cosmic flow, they found something extraordinary. There is, on one side of our sky, a vast region of underdensity, a cosmic void of staggering proportions, hundreds of millions of light years across, where galaxies are scarce and matter is dramatically below average. This region lies almost directly opposite the direction of the Great Attractor and Shapley on the other side of our galaxy, and it has been pushing us all along. They named it the Dipole Repeller because in the dipole of cosmic motion, where one direction is the attractor and the other direction is the repeller, this region of emptiness sat squarely at the repulsive pole. Roughly half of our peculiar velocity, the team calculated, was being driven by the push of this enormous void. The other half was being driven by the pull of the Shapley concentration and the Great Attractor. We were not just falling towards something. We were also being shoved from behind. The river of galaxies we ride was being driven both by the slope it descends and by the high ground it leaves behind. The implication of this discovery is hard to overstate. For decades, astronomers had been asking the question, what is pulling us? The Dipole Repeller paper effectively reframed the question. The right question was not what is pulling us. The right question was, what is the gravitational landscape we exist within? And the answer turned out to be that the landscape has both peaks and pits, mountains and valleys, massive concentrations of galaxies on one side, vast emptinesses on the other. Our motion is the integrated response to the entire topography. It cannot be explained by any single feature. It is the sum of pulls and pushes, attractions and repulsions across hundreds of millions of light years of cosmic terrain. The Great Attractor, mythological and mysterious as it had always seemed, was only one piece of a much grander gravitational architecture. And we had been missing the other piece, because we had been looking at it the wrong way. We had been searching the heavens for masses to explain our motion. We should have also been searching for emptinesses. This realization has cascading consequences. It means that some of the apparent anomalies in the flow data, the motions that did not quite add up given the known mass concentrations, can be partially explained by accounting for the gravitational influence of voids. The Dipole Repeller is not the only one. Other voids in the local universe contribute their own subtle pushes and pulls. The cosmic web is full of these underdense regions, and each one shapes the motion of the matter around it. A complete picture of cosmic flow requires mapping not just where matter is, but where it is not. The voids, the gaps, the absences are as gravitationally important as the structures themselves, and we are only beginning to map them with any precision. There is something philosophically arresting about all of this. For most of human intellectual history, we have thought of the cosmos in terms of what is there. Stars, planets, galaxies, clusters. The visible, tangible furniture of the universe. The Dipole Repeller forces us to think about what is not there, about the vast emptinesses that shape the motion of everything around them, about the way absence can have presence, gravitationally speaking. Our galaxy is being moved not just by the things we can almost see, like the Great Attractor lurking behind the dust band, but by things that are defined by their lack of substance. Empty space on the right scale becomes a player in the cosmic story. The void on one side of our sky is in its way as important to our destiny as the supercluster on the other. And there is a final, more unsettling layer to this revelation. The Dipole Repeller is itself only the largest void influencing our motion. There are others, smaller but still significant, contributing to the overall picture. And the methods we have developed to detect voids are still primitive compared to the methods we have developed to detect mass concentrations. Galaxies emit light. Voids do not. To map a void, you have to measure the absence of galaxies, and absence is harder to characterize than presence. The maps we have today are coarse. Future surveys will refine them. And as they do, the picture of what is pulling and pushing us will continue to shift. The Great Attractor was the first chapter of this story. The Shapley concentration was the second. Laniakea was the third. The Dipole Repeller was the fourth. There will, almost certainly, be more. The cumulative impact of these discoveries on our scientific understanding of the universe has been, in a quiet way, devastating to several long-held assumptions. Cosmology in the late 20th century was built on the foundation of a smooth, isotropic universe. The cosmological principle was not merely an aesthetic preference. It was the bedrock on which the entire mathematical machinery of modern cosmology rested. The Friedmann equations, which describe how the universe expands and evolves, assume that matter is distributed uniformly on the largest scales. The interpretation of the cosmic microwave background as a snapshot of the early universe assumes that the post-recombination cosmos was very nearly uniform. Theories of structure formation assume that small density fluctuations in the early universe grew into the galaxies and clusters we see today, but that the growth process should produce a universe that becomes increasingly smooth as you look at larger and larger volumes. The Great Attractor and everything that followed has challenged all of these assumptions, not by overturning them entirely, but by revealing how much complexity they were papering over. For decades, the working assumption had been that once you averaged over a few hundred million light-years, the universe would look essentially uniform. Now we know that even at scales of 500 million light-years and beyond, there is structure, coherent flows, massive concentrations of matter on one side of the sky and vast voids on the other. The dipole asymmetry in our local universe is not a small perturbation. It is a defining feature. The cosmos in our vicinity has a direction. It has a high side and a low side. It has a preferred axis of motion. This is not what the simplest interpretations of the cosmological principle would predict. And while most cosmologists would argue that on truly enormous scales, scales of billions of light years, the universe still does become uniform, the boundary at which smoothness sets in keeps getting pushed further out as we make better measurements. Each new discovery has tended to reveal that the universe is lumpier and more structured than the previous generation of models assumed. There has been a quiet shift in the field as a result. Where cosmologists once talked confidently about the universe being smooth at scales above 100 million light years, they now speak more carefully. They acknowledge that local effects, the influence of nearby superclusters and voids, can bias measurements in subtle ways. They consider whether some of the tensions in cosmological parameters, including the Hubble tension we mentioned earlier, might be partially explained by the fact that we live in an unusually structured region of the universe. Our cosmic neighborhood, with its great attractors and great repellers, with its coherent flows extending across hundreds of millions of light years, is not necessarily typical of the cosmos as a whole. We may be looking out from inside a particularly textured corner of the universe, and our measurements may carry the fingerprints of that location. Several theoretical pictures that were widely held in the late 20th century have had to be modified or abandoned. The idea that no structures larger than superclusters could exist, once a confident statement based on the limited timescales available for gravitational evolution since the Big Bang, has been refined. Structures like Laniakea, defined not by gravitational binding but by coherent flow, are now recognized as legitimate features of the cosmic web at scales above the supercluster level. The cosmic web itself, the filamentary network of galaxies threaded through the universe, is now understood to be far more structured than early models suggested. Some of the filaments stretch for hundreds of millions of light years. Some of the voids are larger than entire galaxy distribution catalogs from the 1980s. The universe has more architecture than we thought, and the architecture is more coherent than we predicted. There has also been a quiet revolution in how we think about gravity at the largest scales. The Dipole Repeller discovery in particular has forced cosmologists to reckon with the gravitational importance of underdensity. For most of cosmological history, gravitational analyses focused on where the mass was. The voids were treated as background. They were the empty stage on which the drama of galaxies played out. The realization that voids actively shape the motion of surrounding matter, that an empty region of space can effectively push galaxies away in a manner that mirrors the pull of a mass concentration, has changed how cosmologists model cosmic flows. The gravitational landscape now includes negative space. It is no longer enough to know where the matter is. You must also know where it is not. This shift has implications beyond pure cosmology. It connects to debates about dark matter and dark energy, the two great unknown components of the universe. Dark matter, the invisible material that holds galaxies and clusters together, must be distributed in a way that is consistent with the observed cosmic web and its flow patterns. The presence of structures like Laniakea constrains the properties of dark matter. Theories that predict different cosmic web textures than what we observe can be ruled out. Similarly, dark energy, the mysterious force driving the accelerating expansion of the universe, interacts with structure formation in complex ways. The size and distribution of voids depend on dark energy's behavior. As we map voids more precisely, we gain additional constraints on what dark energy can be. The discovery of features like the Dipole Repeller is not just a curiosity. It feeds back into our understanding of the fundamental components of the cosmos. There is also the matter of the Hubble tension, which we have already touched on. This is currently one of the most active areas of dispute in cosmology. The two methods of measuring the universe's expansion rate, one based on the cosmic microwave background and the other based on observations in the local universe, persistently disagree by several percent. Various explanations have been proposed. Some involve new physics, such as additional relativistic particles in the early universe or modifications to dark energy. Others involve subtle observational biases, and some involve the structure of our local universe. If our cosmic neighborhood is unusually dense or unusually structured, our local measurements of expansion could be biased. The mere fact that this possibility is being seriously considered by leading cosmologists tells us how much the discovery of large-scale structures has changed the field. The local universe is no longer assumed to be a representative sample of the cosmos. It is recognized as a particular place, with its own quirks, possibly biasing the measurements we make from within it. What does all this mean for the broader picture of our cosmos? It means that the universe is more interesting than the early models suggested. more textured, more dynamic. The cosmic web is not a passive background to galaxy formation. It is an active, evolving structure with its own architecture and its own currents. We do not float in a uniform sea. We ride a river. And the river has banks and shoals and tributaries and rapids. We are beginning, only in the last few decades, to map the geography of that river system. The Great Attractor was the first major landmark. The Shapley concentration was the second. Laniakea named our home valley. The Dipole Repeller revealed the high ground on the other side. Each discovery has not so much overthrown the previous picture as deepened it, adding new layers of complexity to a universe we once thought was simple. The cosmos, it turns out, is not a featureless ocean. It is a continent, and we are only just learning the shape of its terrain. It is one thing to say that the universe has structure on the scale of hundreds of millions of light years. It is another to ask what that means for us, for you, for me. For the small, fragile civilization clinging to the surface of a small, fragile planet, in one arm of one galaxy, in one valley of a cosmic landscape, we are only just beginning to map. Why does any of this matter? The Great Attractor is not going to reach down and rearrange anyone's life. The Dipole Repeller is not going to alter the price of bread or the trajectory of a career. By every practical metric of human existence, the gravitational dynamics of Laniakea are about as remote from daily concern as anything could possibly be. And yet, there is something about this story that lodges in the mind. Something that quietly changes how you think about where you are. Not in the immediate sense of geography or biology, but in the deeper sense of cosmic location, of belonging, of context. Consider, for a moment, the address we now know we live at: Earth. Solar System, Milky Way, Local Group, Virgo Supercluster, Laniakea Supercluster, the Great Attractor Basin, the Laniakea-Shapley Flow Corridor. Each level of that address is a real, measurable feature of the universe. Each one was discovered by patient scientific work, often by people who would never live to see their findings confirmed. Each one tells us something specific about our location, our motion, our relationship to the wider cosmos. And the full address has only existed in its current form for about a decade. The naming of Laniakea was 2014. The Dipole Repeller was 2017. The picture of our cosmic neighborhood that we now carry in our heads is, in the long span of human thought, brand new. For tens of thousands of years, every person who ever lived had no idea where they actually were on the largest scales. They lived on a world they thought was the center, or one of a few worlds, or one of countless worlds drifting at random. None of them knew about the river they were riding. None of them knew about the basin they belonged to. None of them knew their cosmic address. We are among the first generations to know any of it. That alone is worth pausing over. There is a way in which this knowledge changes the texture of ordinary moments. When you stand outside on a clear night and look at the sky, you are looking at a slice of Laniakea. The stars you see, the few thousand visible to the unaided eye, are all in our own galaxy, but the faint band of the Milky Way curving across the sky is the disk of the galaxy itself, and beyond it lie all the other galaxies of our home structure. When you look up, you are looking out across the river, and without knowing it, your body and your planet and your entire galaxy are moving. Every second, the Earth carries you about 30 kilometers in its orbit around the Sun. Every second, the Sun carries you about 200 kilometers in its orbit around the galactic center. Every second, the entire Milky Way carries you several hundred more kilometers toward the Great Attractor. The motion is continuous and inexorable. It does not stop. It has not stopped for billions of years. It will not stop for billions more. You are at this very moment falling toward something. So is everyone you have ever known. The strangeness of this is sometimes worth sitting with. We tend to think of stillness as the natural state of things. The kitchen table is still. The ground is still. The buildings are still. And in any local frame of reference, this is true. Nothing moves relative to its immediate surroundings, but step back and the stillness dissolves. The planet spins. The planet orbits. The sun orbits. The galaxy moves. The galaxy is pulled. Nothing in this universe is at rest in any absolute sense. We exist in a state of perpetual motion that we cannot feel because everything around us is moving in the same way. The current of Laniakea carries us as a unit. The stars relative to which we measure ourselves are being carried too. The whole landscape flows together, and from inside the flow, there is no obvious sensation of being carried. You have to use telescopes and decades of patient measurement to detect it at all. There is also something to be said about how this knowledge connects to questions of significance. For much of human intellectual history, the discoveries of astronomy have steadily reduced the apparent importance of our place in the cosmos. Copernicus moved us off the center. Galileo showed that other worlds had moons of their own. Herschel and others revealed that the sun was one star among many. Hubble revealed that our galaxy was one of countless galaxies. Each step seemed to make us smaller, less special, more incidental. There is a name for this gradual demotion in some philosophical circles: the Copernican principle, the steady erosion of human cosmic uniqueness. And yet, the discovery of Laniakea and the Great Attractor adds something interesting to this story. Yes, we are not the center. Yes, we are one tiny corner of an unimaginably vast cosmos, but we have a place. A specific place, a real address with definite features. We are not adrift in featureless space. We are inhabitants of a particular gravitational basin, with a particular history, with particular boundaries, in a particular direction of flow. We belong somewhere, and that somewhere has now been named. It has been mapped. It has been studied. For the first time in human history, we know our cosmic neighborhood not as an abstraction, but as a place. This has, for some people, an oddly grounding effect. We are tiny. We are brief. The civilizations we build are flickers on the surface of a small world that itself is a speck in a galaxy that is itself a participant in a flow of millions of galaxies. None of this changes the personal scale of human life. The people we love still matter. The things we build still matter. The small decencies we extend to each other still matter. But there is a frame around all of it now that did not exist before. We know we are riding a river. We know the river has banks. We know there is a destination, even if we will never reach it within any human timeframe. The knowledge does not diminish ordinary life. If anything, it gives it a context. The strange privilege of being here. The strange privilege of being able to know any of this at all. Out of billions of years of cosmic evolution, our particular slice of awareness happens to coincide with the brief moment when the universe became, for us, intelligible. We could have lived in any age. We happen to live in the one where this knowledge began to be possible. There is one more aspect of this story that touches us personally, and it has to do with time. The Great Attractor, the Shapley concentration, the boundaries of Laniakea, all of these exist in our future as much as our present. We are moving toward them. Our descendants, if humanity has descendants long enough into the future, will inhabit a galaxy that has fallen further into the basin. The cosmos is not a static stage. It is a process, and we are part of the process, however small a part. The river carries us forward, and our motion is not separate from the great story of the universe. It is the story. For all that we have learned about the Great Attractor and the larger structures it belongs to, the most honest summary of our current understanding is that we are still at the beginning. The map we have today is dramatically better than the map we had in 1988, but it is still coarse, still incomplete, still riddled with regions we cannot see clearly and questions we cannot yet answer. The Zone of Avoidance, that thick band of obscuration cast by our own galaxy, still hides a portion of the sky from optical observation. We have made impressive progress mapping it through radio and infrared and X-ray techniques, but our census of the galaxies hidden behind the dust is not complete. New galaxies are still being discovered in that band every year. Some of them turn out to be members of previously unknown groups or clusters. Each discovery adds another piece to the gravitational accounting, and each piece raises the possibility that there are more pieces still to find. Until we have a full inventory of what lies behind our own galactic plane, our picture of the local universe will remain provisional. There are several major observational efforts currently underway or planned that will sharpen the picture in the coming years. The Square Kilometre Array, an international radio astronomy project being built across multiple sites in Africa and Australia, will give astronomers unprecedented sensitivity at radio wavelengths. When fully operational, it will be able to map neutral hydrogen across vast volumes of the universe. including regions behind the Zone of Avoidance that have so far been only partially explored. The combination of sensitivity and survey speed should allow for a far more complete census of galaxies in the dust-obscured band, finally giving us a comprehensive view of what makes up the Great Attractor and the structures around it. The Vera C. Rubin Observatory in Chile, which began its main survey operations in 2025, is conducting a deep, wide-field optical and near-infrared survey of the southern sky over a 10-year period. While its primary scientific goals include dark matter, dark energy, and transient phenomena, its data will also contribute significantly to mapping the distribution of galaxies across our cosmic neighborhood, refining our understanding of cosmic flows. Space-based missions are also playing a key role. The Euclid Space Telescope, launched by the European Space Agency in 2023, is mapping the geometry of the dark universe by surveying billions of galaxies across more than a third of the sky. Its primary mission is to investigate the nature of dark energy and dark matter, but the byproducts include extraordinarily detailed maps of galaxy distribution out to enormous distances. These maps will help constrain the structures that contribute to local cosmic flows. The James Webb Space Telescope, although primarily designed for studies of the early universe and exoplanets, can also be deployed to study individual galaxies behind the Zone of Avoidance in detail when the science case is compelling. Future missions, including the proposed Habitable Worlds Observatory and several next-generation X-ray observatories, will add further layers of capability over the coming decades. But even with these new instruments, fundamental uncertainties will remain. The Great Attractor's mass is still estimated to within a factor of 2 or so. The relative contributions of the Norma cluster, the Centaurus cluster, and other components are still being refined. The exact boundary between Laniakea and its neighbors is defined by where the cosmic flow watershed lies, and that boundary is sensitive to assumptions in the analysis. Different methods of identifying watersheds give slightly different answers. The picture is robust in its broad outlines, but the details are still being painted. The question of whether there are additional, even larger structures pulling on us from beyond Shapley remains open. Some analyses hint at coherent flows extending to such large distances that the conventional cosmological framework struggles to accommodate them. Other analyses dispute these results. The community has not converged. There are deeper questions that the next generation of measurements will need to address. The Hubble tension, the disagreement between different methods of measuring cosmic expansion, has not gone away despite years of effort. Some cosmologists wonder whether part of the answer lies in a better understanding of local structure. If we live in an underdense bubble within a larger overdense region, or if our cosmic neighborhood has properties that bias our measurements in ways we have not yet accounted for, then resolving the Hubble tension may require understanding the local universe in even greater detail than we currently do. The Great Attractor and Laniakea are likely to play a role in this resolution, although the precise role is not yet clear. The interplay between local structure and global cosmological measurements is one of the most active areas of current research. Another open question is whether the standard model of structure formation, based on cold dark matter and inflationary initial conditions, can fully account for the architecture we observe. The existence of structures as large and coherent as Laniakea and of voids as enormous as the Dipole Repeller is consistent with the standard model at a broad level. But the precise statistics of these structures, the distribution of their sizes and masses, the frequency with which features at the extreme end of the spectrum should appear, are still being tested against the data. Some analyses have suggested that certain very large structures are slightly more common than the standard model predicts. Others have argued that everything fits within expectations. Resolving these debates will require larger and more complete surveys, and they will be one of the central tasks of cosmology in the coming decades. There is also the question of what lies beyond the structures we have already mapped. Laniakea has neighbors. Perseus Pisces, Coma, Hercules, and other supercluster basins each anchor their own regions of the cosmic web. Beyond these, on truly enormous scales, the universe begins to look more uniform, But the transition from textured to smooth is not as sharp as cosmologists once thought. There may be coherent features at scales of billions of light years that we have not yet identified. There may be patterns in the distribution of voids and superclusters that hint at processes we do not yet understand. The discovery of the Great Attractor and Laniakea did not end the story of large-scale structure. It opened a new chapter, and we are still in the early pages of that chapter. For the next generation of astronomers, the work will be a continuation of what the Seven Samurai began. Patient, careful, painstaking measurement, cross-checking results across different methods, building maps that grow more detailed with each survey, identifying the structures we have missed, refining our models of how matter has organized itself across the visible universe. There will be discoveries. There will be controversies. There will be moments when the data refuses to behave the way the theories predict, and the field will have to wrestle with what those moments mean. None of this will yield a single dramatic resolution. The history of cosmology suggests that progress comes in increments, with each generation adding a layer of clarity to what the previous generation could only glimpse. What we can say with confidence is that the Great Attractor is here to stay as a permanent feature of our cosmic map. It is no longer a mystery in the sense that we do not know if it exists. It is real. It has been mapped. Its components have been identified. The story of how we discovered it is now a part of the history of science, but it remains a mystery in the deeper sense that we do not yet know everything about it, and the more we learn, the more we realize how much we still have to find out. The patient work continues. There is a particular kind of perspective that comes from spending time with this story. Not the technical details, not the names of the structures, not the catalogue of discoveries. Something quieter and perhaps stranger that settles in only after you have lived with the picture for a while. It is the realization that the universe we inhabit is, on the largest scales, in motion. Not just expanding, although it is. Not just full of orbits and rotations, although those are everywhere. But moving as a flowing landscape, with currents and basins and watersheds, with high ground and low ground, with rivers of galaxies all heading somewhere. The cosmos is not still. It has never been still, and we are part of the flow. This realization sits oddly with the everyday experience of being human. The ground under your feet does not feel like it is moving. The buildings around you do not seem to be drifting. The sky overhead seems fixed, with the same constellations our distant ancestors would have recognized. And yet, in the time it takes you to read this sentence, you have traveled hundreds of thousands of kilometers across the cosmos. Earth has moved in its orbit. The sun has moved through the galaxy. The galaxy has moved through Laniakea. Laniakea has moved relative to its neighbors. None of this is metaphor. It is measurement. We are riding a current that we cannot feel because everything in our immediate vicinity is riding it with us. The stillness is local. The motion is universal. There is something humbling in this, but also something curiously expansive. For thousands of years, philosophers and religious thinkers have wondered about humanity's place in the cosmos. Are we central? Are we incidental? Are we alone? Are we accidental? The answers offered have varied wildly across cultures and centuries, often without much hard data to constrain them. The discoveries of the past century, including the discovery of the Great Attractor, have not resolved these old questions in any final way. But they have given us something that previous generations did not have. They have given us a real, specific picture of where we are, not in metaphor, not in myth, in actual coordinates, in actual gravitational basins, in actual rivers of flowing galaxies. We have a location now. We know our cosmic address. And that knowledge, however incomplete, is one of the most extraordinary inheritances any generation has received. Think about what it means that we know any of this at all. The Great Attractor lies more than 150 million light-years away. The light that reaches our telescopes from its general direction began its journey before our species existed. Before the first, Homo sapiens walked the savannas of Africa. Before mammals had recovered from the asteroid that ended the age of dinosaurs. The information we are using to map our local universe is, in a literal sense, ancient. It carries with it the imprint of structures that have been evolving for far longer than the entire history of human consciousness. And we, in a brief flicker of awareness on a small planet, have managed to receive that information, interpret it, and assemble it into a coherent picture. The patience and ingenuity required to do this, across multiple generations of astronomers, is one of the quiet triumphs of human civilization. It does not get celebrated the way other achievements get celebrated, but it is, in its way, as remarkable as anything our species has done. There is also something to be said for the way this knowledge changes our sense of time. Human beings tend to think in scales we can grasp: a lifetime, a century, a few thousand years. The history of civilization, the rise and fall of empires, the slow accumulation of knowledge from one generation to the next. These are the scales on which most of human thought operates. The cosmos operates on different scales. The flow we are riding has been carrying our galaxy toward the Great Attractor for billions of years. It will continue to carry us for billions more. The sun will eventually exhaust its hydrogen fuel and swell into a red giant in about 5 billion years. By that time, our galaxy will have moved much further along its trajectory. The Andromeda galaxy, currently about 2.5 million light-years away and approaching us, will have collided with the Milky Way and merged into a new combined galaxy. The cosmic flow will continue regardless. Civilizations may have risen and fallen on countless worlds. Stars will have been born and died by the trillions, and still the river will flow. This is a perspective that, for some people, is overwhelming. The scales are so far beyond human concern that they can feel almost crushing. What does anything we do matter, set against such vast time horizons and such enormous distances? The honest answer is that the cosmic perspective does not, on its own, give meaning to anything. Meaning is a human construction. It comes from how we live, how we treat each other, what we make of the brief windows of awareness we have been given. The size of the universe does not diminish the importance of a kindness shown to a stranger. The motion of Laniakea toward the Great Attractor does not lessen the value of a quiet evening with someone you love. The cosmos is what it is, and human life is what it is, and one does not have to compete with the other. They simply coexist. The vast and the intimate, the eternal and the brief. Both are real. Both matter in their different ways. What the cosmic perspective does offer, though, is a kind of clarity. When you know that you are riding a river of galaxies toward a destination none of your descendants will ever reach, the trivial conflicts of daily life can sometimes seem a little smaller. The disputes that consume so much human attention may not deserve quite as much weight as we give them. The arbitrary divisions that separate one group of people from another can look, from a sufficient distance, almost incidental. We are all, every one of us, passengers on the same vessel. We share a galaxy. We share a local group. We share Laniakea. We share the current that carries us toward whatever lies ahead. None of us chose to be here. None of us will be here for long, in any cosmic sense. And while we are here, the only meaningful question is what we choose to do with the time and awareness we have been given. There is one more aspect of this story that I want to leave you with. It is the fact that we are, almost certainly, not the only ones asking these questions. The universe contains billions of galaxies. Within our own galaxy, there are billions of stars. Many of those stars have planets. Some fraction of those planets lie in conditions where life is at least possible. Whether any of those potentially habitable worlds have ever actually produced life, and whether any of that life has ever developed the kind of awareness that asks questions about cosmic location, we do not know. But the numbers suggest that the question is worth asking. Somewhere out there, on a world we will never visit, in a galaxy we will never see except as a faint smudge of light, another mind may be looking up at its own night sky and wondering where it is, wondering what is pulling it, wondering what the great structures of its local universe are and where it fits into them. We may never meet such minds. We may never know if they exist. But the possibility itself is part of what makes the cosmic perspective worth holding. We are not necessarily alone in our wondering. The universe may be full of small flickers of awareness, each of them trying, in their brief moment, to understand the river they are riding. There is a moment when you finally step back from all of this, when the names and the numbers and the discoveries settle into something quieter. The Great Attractor, Laniakea, the Shapley concentration, the Dipole Repeller. These are not just labels on a cosmic map. They are landmarks of a journey that none of us will ever complete, and yet every one of us is making. Right now, at this very moment, as you read these words, the Earth beneath you is turning. The sun is sweeping you through the galaxy. The galaxy is carrying you across Laniakea, and Laniakea itself is being pulled, slowly and inexorably, toward something vast and still partly hidden in the dust band of our own sky. You are not standing still. You have never been standing still. From the moment you were born, you have been in motion. And from the moment you read this, you will continue in motion until long after the last person who ever knew your name has forgotten you. The river does not stop. What I want you to take from this is not fear or loneliness or any sense of being lost in a cosmos too large to comprehend. The Great Attractor is not menacing. Laniakea is not threatening. The Dipole Repeller is not actively pushing us away from anything we would have wanted to reach. These are simply features of the universe we happen to inhabit. They are part of the architecture of home, even if the architecture is on a scale we cannot fully wrap our minds around. We did not choose this home. We did not design it. We woke up inside it, and we have spent the last few thousand years slowly, patiently learning what kind of place it actually is. And what we have learned is that it is structured, it is vast, it is in motion, and it is, in its way, beautiful. There is a strange beauty in the fact that everything in our cosmic neighborhood is flowing together toward the same gravitational center. There is a strange poetry in the realization that even the emptiness behind us is shaping our path forward. The cosmos has form, it has direction, and we are part of it. Take a moment to consider what we have managed to do, as a species, in coming to understand any of this. For most of human history, the question of where we are in the universe was answered with myth. Stories about the sky and the gods who lived in it. Pictures painted by people who could not have known the true shape of what they were looking at. Then, very slowly, beginning a few centuries ago, we started measuring instead of guessing. We built telescopes. We invented mathematics that could describe the motions we observed. We sent instruments into space. We built radio antennas large enough to detect whispers from across the galaxy. We trained generations of scientists to look at the data carefully, to question their own assumptions, to be willing to be wrong, to refine their understanding step by patient step. The story of how we came to know about the Great Attractor is, in its small way, the story of what humanity is capable of when it commits itself to understanding the world. It is the story of curiosity over centuries, of careful, often unglamorous work, of generations passing torches to generations. None of it has been quick. None of it has been easy, but it has worked. We know things now that no one knew 100 years ago. And the people who will live 100 years from now will know things we cannot yet imagine. And here is where I want to leave you, with the awareness that the silence behind the Great Attractor, the obscured region of sky that has hidden it from our direct view for so long, is not really silence at all. It is a curtain that we are slowly, year by year, pulling back. Every new telescope, every new survey, every new generation of careful astronomers is adding pieces to the picture. The thing on the other side of the dust band is no longer entirely hidden. We have seen its core. We have measured its mass. We have mapped the cosmic basin it anchors. The mystery has not vanished, but it has changed shape. It is no longer the mystery of whether something is there. It is the deeper mystery of what it all means, what the architecture of the cosmos says about how the universe organized itself, what the flow of galaxies tells us about the underlying physics, what it means, philosophically and personally, to be a temporary, conscious traveler on a river that flows across billions of years and hundreds of millions of light years. These are questions that no single video, no single book, no single lifetime can fully answer. They are the kind of questions that humanity will keep returning to, generation after generation, each time with slightly better instruments and slightly clearer maps. We are part of a long conversation. The Seven Samurai joined it in the 1980s. R. Brent Tully and his colleagues advanced it in the 2010s. The astronomers using the Square Kilometre Array and Euclid and Rubin will advance it further in the coming years. And somewhere out there, in some future generation we will never meet, someone will look at the work we are doing now the same way we look at the work of the early 20th century, with gratitude and with a sense of how much further there still is to go. I want to thank you for staying with me through this long exploration. It is a strange thing, in the busy world we live in, to set aside the time to sit with something as enormous and abstract as the gravitational architecture of the local universe. But I think it matters. I think the perspective is worth holding on to, even if only occasionally. The next time you stand outside on a clear night and look up at the stars, remember what is happening. You are not just looking. You are moving. The ground beneath you is moving. The sun and all its planets are moving. The entire galaxy you live in is moving. And somewhere, beyond the dust band of the Milky Way, in a region of sky we cannot see directly but whose pull we have measured for nearly half a century, lies the gravitational anchor of our cosmic home, the Great Attractor, pulling us quietly and steadily across the cosmos, as it has been doing for billions of years, as it will continue to do for billions more. If this journey through the unseen architecture of our universe meant something to you, please take a moment to like the video. Subscribe if you have not already. Share it with someone you think might find it as fascinating as you did. And in the comments below, tell me where you are watching from. I love seeing the names of countries and cities scroll past, and knowing that the same questions about our place in the cosmos are being asked by people in every corner of the world. We are all riding the same river. We are all citizens of the same Laniakea. And we are all, every one of us, falling toward the same hidden heart of our cosmic neighborhood. The Great Attractor pulls us together in more ways than one. Until next time, keep looking up, keep wondering. And remember that the universe, for all its silence and all its mystery, has been quietly answering our questions, one careful measurement at a time. We are not lost. We are just very small, traveling through something very large. And that, in the end, is one of the most wonderful things about being here at all.